Yeah, I think we're right about 1 o'clock here. So
Sounds
I
good.
do see quite a few people have joined here. So maybe we'll get started here. So my name's Bennett Howard. I'm a sales engineer for Sodick here. I'll be kind of doing an introduction here. You've got from our side Len Hampton as well on the top of your screen. He's the national sales manager here. And then Weston Harbaugh will be our host, also a sales engineer from Sodick, covering a different area of North America here. So with that, we are lucky to have Brandon Birchmeier here from iMFLUX. I've been promoting it last couple weeks, but it seems we get a ton of questions. And a lot of people are curious about this technology and where this company is headed. So super excited to have you here, Brandon. Just to do a quick introduction here, Brandon is the Technology and Innovation Director in iMFLUX. Looks like just about 20 years of injection molding, hands-on injection molding experience, and quite a breadth of knowledge from automotive, large automotive to packaging and kind of everything in between. So I think we'll see some interesting perspective because of that. So with that, maybe I'll hand to Weston here real quick. He's going to talk you through Q&A and how he's going to handle that, and then we'll get started. So thanks everybody for joining.
Great, thanks Bennett. And just to I think cover that, Bennett Howard is our regional sales engineer for Minnesota, some of Wisconsin, and then the Southwest America, right? Sometimes he gets in and maybe doesn't get the credit he deserves on a lot of the stuff we're doing. So thanks, Bennett.
Thank you.
And thanks everybody for joining us today as we partner here with Brandon from iMFLUX. I want to take just a couple minutes to cover a couple quick logistical items. Okay, first is Sodick and Friends webinar. As Bennett mentioned, this is number 23. We started in March of 2020 and have had really great success. Have had a lot of great topics and a lot of great partners, which there's no slowing down with that. Over the next couple of months, we have a great lineup coming up. Includes Penn State, Barron's, RJG, and more. And secondly, and most importantly right now, let's let Brandon get through his presentation fully today. If you have questions, or once you have questions, send those in. On the lower right-hand corner of your screen is a Q&A section. Direct them to myself as the host. As Brandon finishes, and I will go ahead and address each question as they come in. We'll ask them to Brandon and provide him ample time to answer each one, okay? I guess, Brandon, with that, the show is all yours. Take it away, man.
Okay, well, thank you very much. Thank you to the Sodick team for allowing us to participate in your Sodick and Friends webinar series. Looks like it's great to have the industry come together, partnerships to kind of share how things are advancing in our industry and kind of new thoughts and new ideas and how to implement them potentially in your own organization. So my name is Brandon Birchmeier. I'm the Innovation and Technical Director here at iMFLUX. And I'm going to talk about the green curve today, how we do our low constant pressure molding and a lot of the advantages you can take from that, specifically with kind of a hint towards the sustainability side. So we will dive right in. Like Weston said, please drop those questions you have in, and we'll be happy to answer those at the end of the presentation. So let's dive in. So the green curve, it's a very different way to how I was taught how to mold. A lot of people approach molding, how a lot of injection molding machines are kind of set up to be utilized. And it's a big change here, and change is hard. As many of us in the industry know, it's not always easy to change your thinking, your thought process, and especially how you do things day in and day out from an injection molding standpoint. But I want to talk, today's going to be about explaining how we're different, why we think there's some significant advantages to this approach, and how you can maybe take advantage of those yourselves in your facilities. So let's start with the conventional high pressure molding process. Hopefully this curve isn't new to many of you watching, but this is graphing plastic pressure. So this is true plastic pressure we're measuring at the nozzle of the machine over time. And at a constant rheology-based injection velocity, what you'll typically have is that fill pressure increase over time, as you're seeing, until we hit that transfer point into your pack and hold phase, where you'll then control via pressure, a certain amount of pressure for a certain amount of hold time, and then you go into your cooling phase of your process. So we talk about decoupled molding. You're decoupling the velocity fill stage from the pack and hold stage, and you get from one to the next via your transfer position. iMFLUX is a different approach. The process we just talked about, your conventional process, the fill stage, pressure is an output of the process. It's not necessarily an input. You're telling the machine how fast you want to inject. iMFLUX doesn't do that at all. We never tell the machine how fast to go or how slow to go. All we do is control pressure at the nozzle, and typically at a lower constant pressure. And it looks very similar to what you're seeing there in the graph, that green curve, much lower pressure. We don't have phases. We're not transferring from a fill stage to a pack and hold stage. And I'll explain how we are able to accomplish all that. Overall, we do fill your parts slower. You can see where your 90% fill is in your traditional conventional molding process, right? You're transferring at that 90-95% full stage. With the iMFLUX process, that happens much later on in our filling process. However, we do not require a pack and hold stage after filling is required. So we actually get some faster cycle time savings here, because if you look at it from an inject forward standpoint. So we fill slower typically, but we don't need all the pack and hold pressure to compensate for all the filling we did on the front part of the process. Next thing we're going to talk about is the pressure versus velocity relationship. And this is really important. Like I mentioned in the prior slides, in your conventional process today, you're telling the machine at which velocity you want to inject that. And the pressure is a result of that velocity until you transfer. So you get a relationship that looks very much like so, right? Your machine's getting up to that constant velocity. As it maintains it, the pressure in the system continues to climb until you transfer. The velocity drops out during our pack and hold phase. iMFLUX is a very interesting velocity profile. So at constant pressure, I mentioned we fill slower, but we're not always filling slow. As you'll see comparatively here, at that lower pressure, my velocity as I'm approaching my pressure set point is actually pretty fast. We do want to still take advantage of the shear thinning properties of the polymer, but we don't believe we need to do it for the entire 90-95% of the part volume. So what happens here is we get a hyperbolic relationship in velocity until we hit that pressure set point, and then we begin a parabolic slowdown in the velocity. The parabolic slowdown you're seeing in that velocity is allowing us to pack that part out while we fill it. It's during that controlled slowing, and as you can see, we always get this parabolic relationship, especially in a constant nominal wall thickness. As that velocity slows down, we are able to pack that part out, which doesn't require us to have to transfer over into a pack and hold phase. That parabolic slowing down is actually packing that part out while we fill it out. You get a lot of advantages, which I'm going to cover. The first is you can do some pretty wild things when you always allow the plastic to be in control, which is what's happening here. So in this part here, this is one of our impossible parts that has been featured in Plastics Technology. We've had it at trade shows as well. What you're seeing here is a pretty big, typical sprue system that goes down to a 3-inch long, 30 thousandths diameter runner system. So it's like a thread for a runner. Then goes back into a subgate into a full part. We built this on purpose because you can't mold this traditionally. As soon as you hit that very small gate section, gate thread, your part wants to flash, right? Because what are you doing? You're telling your machine how it needs to operate, strictly from the machine standpoint, with little regard to what's happening in the plastic. So if you tell that injection molding machine to inject that 2 inches a second, it'll do that, but you're going to flash that small runner. What happens with the iMFLUX process is geometry is dictating our velocity. So at a constant pressure, I'm filling that large sprue out pretty quickly. You can fill out pretty quickly. There's not a big resistance to fill there. But as soon as I hit that thread gate, I slow down dramatically, and we slowly fill through the runner system to reach the thick section and then speed back up again. That geometry, because I'm controlling that constant pressure, that geometry is dictating my velocity. So the machine automatically slows down when it needs to slow down and speeds up when it needs to speed up. And your part's in control. This is, the very different part of our process is the plastic in the part is always in control of the machine. At no phase during the filling of this part is the pressure of the plastic not in control. The plastic's always in control. And we're allowing the mold and the plastic to actually dictate the process through low constant pressure. So it allows you to do some crazy things. One of those is we can pack our parts out as we fill. If any of you with small kids like me may recognize these are your Pampers wipes lids. Just shows a short shot comparison of your conventional molding process versus the iMFLUX process. Our short shots don't have the sink marks, the orange peel, things you would typically expect of your short shots. And our philosophy is pretty simple. Why create the defects and go back and fix them with extra time and pressure, which is basically what's happening in your conventional process. Once those parts are filled, you now need to fix everything you created during the filling, all those sinks, all the orange peel. You need to pack that part out, right? That's what we transfer into a back and hold stage. However, if you fill and maintain constant pressure in your process, those parts will actually pack themselves out while that flow front progresses. So now I don't have to go back in and fix the sink or fix the surface appearance after the fact and after transfer. Now it's happening while that part's being filled out. How does this work? So we got this neat animation that kind of demonstrates this for you. On the left is your conventional process. And what I want you to recognize is what happens at transfer. And this is important. So as you're skinning your layer of polymer across the cold mold steel, and as you'll see in the animation, you're getting this skinning. And once you transfer and you get a little bit of screw bounce or something, there's a relaxation of that thin wall section, that thin area, that skinned area, and then it's reapplied to the surface. So if you deal with things like hologramming, tiger striping, things like that, it's coming from the fill and transfer portion of your process, where you're applying the plastic to the surface of the mold, allowing it to relax and then repressurize. And in the iMFLUX process, our frozen fraction, as you can see, is much, much thicker because we're operating at much lower pressures. And I'm not screaming at high injection speeds to the end of fill or to 95% of fill. I'm allowing the part to pack out while it fills. And since there's no transfer, we never allow that surface to release from the mold steel. It's always at the mold surface. So things like the hologramming and whatnot don't show up in your final part. This next cool animation is just showing how geometry is dictating velocity. And here's a great example. And being a wholly owned subsidiary of Procter Gamble, we have lots of living hinges, as you can imagine. This is kind of showing how a living hinge would impact the process, right? Traditionally, if I was just molding, you would need to do a short shot series, maybe even install sensors, understand where the flow front is before or after that hinge, that thinned out section. Maybe you do want to slow down or do something in your process to compensate. Again, with the iMFLUX process, as I see those areas of more resistance or less resistance, I will make up for that in velocity. So once I see that choke point, my process will actually slow down a little bit through the living hinge, and then speed back up to finish. Again, it's always auto-adapting. We've heard the term, molding from the plastic's perspective. This is it right here. The plastic is always in control of the process. At no point in time am I relying strictly on the mechanics of the machine. We're always listening to the plastic and the mold to dictate the process. And as the things change in the part, we're able to compensate for those in real time without sensors in your actual tool. I'm just installing a sensor at the nozzle of the machine to pull this information out. So how does this work? Here's a great example. Any of you ever use Crest toothpaste? Here's one of our caps. But what I want to show you here is kind of what happens to screw velocity in a constant pressure process. So here you can actually see, I'm going to play this again. As we're filling this out, I'm coming up as I reach my pressure set point, and then it slows down as it hits that living hinge. And then as I go past the living hinge, it'll speed back up again. And then the part we get the parabolic slowdown like we discussed earlier, right? We want that slowing down. That's when we're going to pack that part out while we fill it out. One issue with a part like this on the living hinge is you'll have a very high pressure side where your gate is and a low pressure side where your hinge is. Because the machine doesn't know any better, right? It's just doing what the operator's telling it to do. Now that geometry of that part has feedback to that system. If we want to talk about closed loop control, here it is. We're closing the loop around the material during every phase of the injection molding process. No other technology can do that. And the velocity, right, as you can see, the velocity is varying based on geometry. So one area of sustainability interest is weight reduction. And here, it's very common for us to get 1 to 3% weight reduction. We talked about that high pressure differential as well in the conventional process. And you can see it even in the simulation side of things, how much more pressure you're seeing on the gate side of that product versus the living hinge side. Influx process, right? I am not continuing to pressurize that part at a constant velocity. So those pressure differentials between the lid and the base or the gate side of the part are much more uniform. Also, that 1 to 3% weight is typically happening while you're trying to achieve your gate seal. When you're transferring your process and you're using hold time and hold pressure, you're actually putting a little, it's not like you're moving a little bit of material as you're waiting for that gate to freeze off. That weight is usually about 1 to 3% that we're not putting in because we don't need the excess time to achieve gate seal. Again, you're going from a very high speed process to a pack and hold phase. You have a much larger gate orifice to seal off versus the influx process where we're using very low shear and very low velocity at the end of our process where gate seal is almost immediate. One of the neat things about our technology, and what I love to talk about, is our auto viscosity adjust technology, which I'm going to start talking about now. So what's really interesting about using constant pressure in a barrel is it now mimics a rambler. If any of you have gone out and tested MFI of your material, that test is done with constant pressure. It's not done with constant velocity. We actually use constant pressure to determine the melt flow index of the material. Well, I'm basically turning your barrel into a large diameter. Because I'm utilizing constant pressure, if I recognize these changes in the fill rate, I know something has happened in the viscosity. So I'm able to recognize those changes in real time and adapt to those changes in real time, which gives our technology some very unique advantages, especially as we start talking about recycled resins, sustainable resins, more wide spec resins. So how does this work? So we'll go back to our cap that we had, the toothpaste cap. And the way this works is, right, we'll set up our initial process that we're happy with. However, as viscosity changes, you can see what we'll do is we'll recognize the change in viscosity of the material and automatically adapt the driving pressure. But what remains the same is that velocity profile. So I can, modulate the pressure up and down to maintain that constant velocity profile. And this shape is important. This shape's dictated by the geometry of the part. I'm not telling the machine, what the shape should look like, the velocity. That's literally dictated by the part in the mold. It finds how it wants to fill, and then we'll just modulate the pressure in real time based on the material. So let's see this in a real live video. So we're going to see here, this is we call our Fakuma mold that we showcased at the Fakuma show a few years ago. And what we're doing here is we're transitioning from a polypropylene to a highly blended polypropylene. We've even done this where we've gone from a polypropylene to an ABS. We've done massive shifts in viscosity. Here you can see that's happening in real time. The process is adapting to the material. The other thing we can do is just block cavities. Remember, we're not going from a shot size to a transfer position. In this 4-cavity mold, I can run 0 cavities, 1 cavity, 2 cavities, 3 cavities, 4 cavities. Those part weights remain the same. My process has not changed. I'm just using a certain amount of pressure for a certain amount of time. I'm not asking the machine to go from a mechanical shot size to a mechanical transfer position, doing whatever it takes to get there. Here, we're just using pressure. And I can, we have 4-day cavity tools that we can run 1 cavity, and my process does not have to change. Pressure is pressure to the mold. So if you're running very high cavity molds, BG has quite a few of those, as not a surprise. And we have tooling damage or maybe a manifold issue, we're able to quickly eliminate those cavities and not actually have to make any process adjustments to accommodate. We don't have to change the shot size. We don't need to change the transfer position or the injection velocity. We can just continue to process the way we had it. And what's this mean for some customers? So I wanted to bring a few examples and talk about. One is Ags Technologies. If you're not familiar, they are a world leader really in using recycled feedstock themselves and actually turning that into automotive parts. They do a great job of bringing in, they even sort, grind, and will recreate the recycled feedstock they need to run their process. As you can imagine, there's a lot of variation in that feedstock, and we help them manage that viscosity. And as you can see, 85% scrap reduction from the since they started using iMFLUX, which is just a massive amount of scrap rate reduction. They don't need as much clamp force, right? We're operating at lower pressures. They even saw some cycle time reduction. So again, where they're using a heavy amount of post-consumer regrind, we're able to accommodate that in the process through our algorithms and auto viscosity adjust, automatically adjust the process in real time so they continue making good parts. Another great example of this is Graystone Logistics. They specialize in highly recycled pallets, things like that, where again, feedstock's very highly variable, and they had to make frequent process adjustments. Here they're seeing, the scraps baked in, but up to 24% increase in throughput, 30% energy savings because they're using, again, that less pressure and that weight savings as well. And they're replatforming iMFLUX across the entire factory, just because they don't need to babysit their machines anymore. They can put in whatever they have available, and the machine will automatically accommodate the material for them in real time. So change is hard. It's a worthwhile endeavor, we think, especially as you're trying to hit your sustainability goals going into the future. You can start to understand how you can get a lot more design flexibility and material flexibility. I showed you that impossible part where we were basically using a thread as the gate system. Gating thick to thin, things like that. We aren't bound by as many rules that you typically find in the conventional molding process. Where your material needs to be very consistent. You need to have a very well balanced tool. All these things of idealism. Unfortunately, for a lot of us that work in factories and production environments, that ideal scenario goes by the wayside, soon after launch. So we're trying to create a better, more intelligent way to manage the injection molding process for you. So you can start using more wide spec resin or be more flexible in your part design and your sustainability solutions. So thank you. That is a lot of information. I'm hoping we have a lot of questions we can go through. And I want to thank the Sodick team again for letting us kind of explain iMFLUX quickly for you, explain how it works, and hopefully how it could be a benefit for your industry or organization as well. And there's my contact information if you have any questions for myself.
Excellent, Brandon. Thank you very much for the presentation and all the information shared. We did have a number of questions come in, so I think we'll get started right away here, okay?
Okay, great.
Number one, first question came in, says, can I just run my molding machine pressure limited or strictly in hold phase and achieve the same results as the iMFLUX process?
Not easily. And I have a few slides here that'll kind of help explain this a little bit, because it's a common question. First and foremost, machine pressure and plastic pressure are not great. One of the first things we learned in our first plastics class is how plastic's non-Newtonian, and we need to think about how it reacts. And then we use hydraulic pressure to predict plastic pressure, which is probably not great. So the first thing we have to appreciate is, hydraulic pressure and plastic pressure. Unless you are in a completely pressurized scenario, then it's hard for one to predict the other. Where it really struggles, though, is on the fill side. Once that mold is completely full and pressurized, it's much more accurate reflection of what the plastic's seeing. But during the fill phase, it struggles to do that. And this kind of just shows you what machine versus plastic pressure would look like typically. This is why we want to control that plastic pressure, because it's much more sensitive to the geometries that we're going to, what happens to that plastic and on a millisecond level as it's going through the mold. So we want to pick that up as quickly as possible and with the most sensitive equipment as possible. And that's getting that sensor actually in the melt. more reasons for that, actually. One is, another thing is tuning. You know, it's very typical for a molder to not have the ability to adjust the tuning on their injection molding machines, which, I mean, that's for good reason, right? You know, if you're going to set your machine up to fill with high injection speeds, that's probably how you'll have your machine tuned. That's not going to work with our process. We actually have to have customized PID tuning loops to get the process to control how we want to. We don't want too much overshooting or undershooting. And a lot of times the tuning that comes with your press isn't adequate to control the pressure we're looking to control. Next thing is PFA. So we have an interesting part of our process we call PFA, or process factor A. And this is to help to adjust to accommodate real-time changes in viscosity. So think of this like if I have a cavity pressure sensor in my mold or not, and I want to get to a lower pressure at end of fill. Let's say I'm molding a Frisbee, for example. And as my flow front gets farther away from my gate, the speed wants to increase, actually. So we need to tamper the pressure down a little bit because the flow front's growing exponentially. And PFA would be one way of doing that. This allows us to adapt that pressure in real time based on cavity pressure feedback or something else in the process. So we won't be able to have we would not have this ability if the machine was driving the process itself. And lastly, just wanted to show this, the versatility that we can do. So I mentioned, you know, constant pressure molding. This is our go-to curve that you'll typically see. However, we can ramp the rate at which we get to those set points as well. So if we want to get up to pressure very quickly or very slowly because of the geometry of the part, we have that ability. So again, more versatility and flexibility of the setup with the process. And that's why you really need a iMFLUX box to get the machine to react how you want to, and you can't just rely on the machine controls.
Excellent there. So outside the iMFLUX box, what other hardware may be needed? And maybe some of these questions you'll want to follow up directly, Brandon,
Sure.
but can it tie into any machine, the hardware, and what would that cost be?
Yeah, so we can, it works on any machine. I think our oldest we've done is like a 1978 press. But the nice thing that even with the older hydraulic machines is a proportional valve is a proportional valve, and that's what we're going to control. So on the hydraulic side of presses, it's very, very straightforward. As we've gotten more into servo-driven pumps and electric machines, there are some more considerations in order to control those, but we work with the like Sodick or other OEMs to make sure you get the adequate control you need, whether it's a hydraulic machine or electric machine or a hybrid. So we can get it to work on any press. As far as hardware, there's three big components. The heart of our system is the sensor that we install at the nozzle. That is how we get our pressure feedback, and that's what we're going to want to react to. And we create an adapter that goes between the end cap of the barrel and the nozzle of the machine, where we'll put a penetration in to measure that plastic pressure. The next thing you'll get is a black box. It's just a little black box, just like we say. And that's to talk to, get the feedback from the sensor, and then also provide the control to the machine and to the screw so that the screws operate at the right velocity we need it to maintain that constant pressure. And then the third piece is you would get your own HMI interface to set up your processes, control your processes. iMFLUX will only influence the injection portion of your machine. Everything else will remain exactly the way it does today. You'll still control your clamp, your recovery, your barrel temperatures, all through your native press.
Excellent. Now, where you are tying into the machine, Brandon, would that void warranties of the machine?
It doesn't. Again, this is where we want to work with the machine manufacturer to make sure everything is they're happy to, and so that isn't the case. And for the most part, we haven't had any difficulties. We've worked pretty well with the OEM, so we have to learn to do that and make sure that they're comfortable with what we're doing as well. So we make sure everyone is comfortable with the situation and the scenario that the machine is put under, so that we don't have to go through voiding warranties and things like that.
Can you comment about the flow front velocities in the cavity during fill and maybe the effect of slow constant machine pressure?
Yeah, so so that great question. And I'm going to go back to a slide here, so bear with me. I'm just going to go all the way to these curves right here. So in your conventional molding process, right, everything is based on from the machine standpoint, right? You tell your injection molding machine to inject that 2 inches a second or 3 inches a second. That's what that barrel is going to do. There is a drop in that velocity as that material is traveling through the mold, you know, through those pressure drops and whatnot. And so the velocity is dictated by the geometry to a small degree. Mostly you see the pressure, but the machine doesn't know any better, right? It's just going from point A to point B at the prescribed velocity you tell it to. With the influx process, that velocity will always be managed by the part and material. So there is a minimum pressure threshold here. I think that's important to recognize. Like, you know, there is a minimum amount of pressure I need to fill that part out. Once we find that, though, and you get the parabolic relationship you're looking at here, that flow front velocities is going to vary very much like you're seeing in that curve, right? We're going to have high injection speeds at the beginning. Once we get up to that pressure set point, we're going to start slowing down parabolically, just like you see in this curve here. That slowdown allows that thick layer that is against the mold steel to remain there. And we have a much smaller channel that we flow through that was shown in the one illustration here. Right, so our frozen fraction is much thicker than you would traditionally see comparatively in the conventional process. But also then there's no transfer. We're never allowing the plastic to relax away from the steel. That's a reason for a lot of defects you typically see on the surface of your part. So the velocity, to get back to the root question, is dictated by an influx. It is completely dictated by the part once we find the critical pressure needed. In the conventional process, it doesn't care about the part at all. Your machine's going to do exactly what you tell it to do, right? Even if you told that, you know, it might be a small part, but if I tell the molding machine to go 10 inches a second, it'll do it. It might create some havoc as it does it, but it'll do it. Influx won't. If I blocked off all of my cavities, influx just won't even inject. It'll build pressure immediately and just stop. So there's always feedback. And that's the important thing we want to get across here is that, you know, with the influx process, we are closed loop around the material in the mold the entire time. Now the mold matters. Typically, your molding machines are agnostic to what's between the plants. It just will do what the operator asks it to do. Influx is very different. Now that mold is in direct control of that material, and it does matter about the geometry and everything else. Probably a long-winded response.
No, that's great. That's what we want to hear. Next question for you. Does the influx process only work on certain types of resins?
No, actually. We've had a lot of success. Obviously, within P&G, we do a lot of olefin work. But in the automotive sector, you know, we've done polycarbonate, ABS, PC ABS, nylons, glass-filled nylons, carbon-filled nylons, ASAs, and you know, rubbers. There are things out there that we definitely have not come across or ran yet, but I would say as far as your general purpose resins, that we've pretty much done everything across the board, and we're able to see comparable results across as well. Now, some things are more challenging than others. If you're trying to bury glass in a highly filled glass part, for example, there's things you want to take into consideration. But in general, the process applies across the board, across all the resins.
You just touched on actually the follow-up question to that is, can you talk a little bit about the limitations in some of those materials, the filled resins?
Yeah.
Or highly nucleated.
Yeah, so well, let's take glass filled nylon, for example. One of the ways you bury glass, right, is with speed. So the skinning you get in the conventional process throughout actually helps you bury that glass a little bit. It also explains why we can get a little bit better weld lines, but I'll save that for a conversation for another day. But by going fast, you bury the constituents or you bury the fillers in the part, which is good when you're trying to get that appearance. Not great when you're trying to have nice, even distribution of all the constituents in the polymer. But the way you do that is through skinning, right? You skin, you go fast, and it helps bury that nylon. Our process towards end of fill likes to slow down. As I explained, that's how we get our pack as we fill. And if that's the instance, we would either operate at higher pressures than we typically would, or we could ramp our pressure profile as needed to compensate for those scenarios. So, there's still lots of flexibility built into our system. But that would be a good scenario where you may get away from just a constant pressure process the entire time, is on a heavily filled nylon where you do want to bury glass or something similar.
How about with LSR molding, Brandon? Does it work with that?
Good question. We have not attempted yet, to be honest with you. So we have lots of things on our docket, as you can imagine. LSR is certainly one of those. I need to get a machine in our R&D lab so I can play around with it a bit more. But we think there will be benefits, but I don't have any real life examples to share just yet.
Next question here. Does it only work on certain geometry parts?
No, not. If anything, it should expand what's capable, especially if you think about your gating locations, things like that. Typically we talk about gating thick to thin. A lot of that's because of how we control velocity in a conventional molding process, and the machine not knowing any better. You can gate influx thin to thick, thick to thin, any way you want, because that geometry will automatically dictate the process all the time. So it'll slow down when it needs to. It'll speed up when it needs to. You don't need to go in and profile all those velocities for it. So that's one big area of advantage there as far as flexibility. But even we can get away with fewer gates, for example. Again, if you're think about an automotive door panel, maybe today you're molding that with 8 gates. Influx possibly could do it with 2 or 3. So you start to see where those benefits elsewhere too. So fewer gates, fewer weld lines, things like that. I would, if anything, I think this gives you more flexibility in your part design, not less. In family molds, I should touch on family molds. Family molds are completely fine with the influx process. We've demonstrated those time and time again because cavity balance isn't so critical to our process. Think in a conventional molding process, why cavity balance is so important. It's because, I'm going to go back to my graph here. Why is cavity balance so important typically? It's because of that pressure rising at constant velocity. So let's say I have an 8-cavity mold. That first cavity to fill is going to see more pressure than the last cavity to fill because of that relationship. The pressure continues to climb at a constant velocity. So those cavities are different from one another because they fill different. With an influx process, it's not nearly as detrimental. I'm filling all those cavities at the exact same pressure. So even if a cavity fills first or second or last, they're all seeing the same driving pressure. So you're going to get much more normalized and closer distribution between all those cavities, which we see is a huge advantage to the process, especially across those high cavitation tools. But also, you can get creative on the family mold side. I do not need to have very good balance in my process at all because I'm not worried about transferring. I'm just going to, we just did a webinar not too long ago, molding a couple bowls, a lid, and some forks and spoons. Completely different, is a 7-cavity mold. Every single cavity is very, very different from each other. But constant pressure allows me to mold all of those cavities without issue. I don't have to worry about all the balancing because I don't have to worry about the pressure continuing to increase on rheology-based injection speeds.
Wonderful. I just got a question here, Brandon, back to the material side.
Sure.
We talked about a lot of the thermoplastic, a lot of, LSR, but how about thermoset materials?
We've done little, not a ton, very little. Again, we've had the same general benefits, but I would say our opportunities have been pretty small up to this point with thermosets. But I have no reason to believe that it would be from what we've learned, we have no reason to think that we wouldn't be successful with thermosets as well.
If you were moving molds between different machines, right? How does that impact your process?
Boy, does it get a lot easier. Think about this. The whole process now is based on plastic pressure and nothing else. As long as I got enough, enough of a shot size, I should be good. Now, let's take that. Let's say let's use the process for. Let's say I'm running this part at 5,000 psi, and I'm doing it in a 100 ton press. I'm going to move that mold to a 200 ton press with the barrel twice the size. I'm still going to mold it at 5,000 psi. I just need to have adequate shot size. I don't need to tell it how fast to go. I don't need to tell it when to transfer. I don't have to do all that math. Right? I just set the process up. We'll turn our AVA on so we get that, we want to get that velocity profile, kind of like we mapped originally. Get close to there, and then you should be off and running. Again, it's plastic pressure. That's what matters here. So moving molds between machines is actually extremely simple. Even building prototype molds becomes way, way easier. I can actually use now the same process on my 1 cavity pilot tool as I can on my 48 cavity production tool. It's the same exact process. It's just pressure and time. So scaling things becomes easier as well as moving things, because everything's not tied directly to the machine, right? Everything is not tied directly to the plastic and directly to the tool.
How does the use of cavity pressure sensors impact the ability to create and maintain a process?
Yeah, let me go back to some of my extra slides here. So the neat thing with cavity pressure sensors is our ability to react to them, kind of like you would in a traditional sense, right? So today, cavity pressure sensors are typically used for the ability to transfer. We'll use it in our PFA response, like I mentioned before. So here you can see the dotted white line is cavity pressure. So as I'm recognizing cavity pressure, you can see PFA mirrors the pressure. So as that pressure rises, it mirrors it in an opposite direction and to the same degree. So if I'm experiencing the pressure in the sensor a little bit sooner, I'm going to react a little bit sooner. If I'm seeing it a little bit later in the process, I'm reacting later in the process. It's another closed loop piece that we can tie into our process. Cavity pressure sensors are not required for iMFLUX to be successful, but if you have them, we will use them. It makes the process a little bit better, be able to react in real time to those actual cavity pressure responses. So we're fans of cavity pressure sensors, but it's not a requirement in order to take advantage of the iMFLUX process.
So how do you adjust the system, the low pressure you fill, if there is issues in the parts?
So adjustments come a few different ways. So if I was an operator, let's say I'm making a short shot, it would be easy as increasing my driving pressure in the process. If I'm molding at 55 or 5,000 psi today, maybe I'm going to mold at 5250 and it fixes that short shot. Ideally though, once we set our curve up for you and we turn auto viscosity adjust on, it automatically makes those adjustments for you in real time as you're starting to deal with not only changes in your resin, but changes in your environment, maybe changes in your manifold. Again, all of those things are driving our process. So as we recognize changes in the environment, so basically anything that impacts my fill time that I would expect at a constant pressure is going to make an adjustment if I'm getting away from what I anticipate. That's really how the auto viscosity algorithms work, is always driving the process to where we know we can be successful, recognizing when that happens and then making the appropriate adjustment when it's needed. And that's AI, recognition of a change, adapting to the change. And that's ultimately what we want iMFLUX to be, a complete autonomous solution for your injection molding shop.
A few of these might be similar or repeat questions, but I want to make sure if they're still asking them that everybody gets the answers.
Sure.
Right? So as far as on the molding machine, what is required, right? What capability must the machine have?
Well, hopefully it's working okay. I would say our biggest thing is, make sure you got enough injection velocity. If you're very limited on the velocity or pressure side, we may not be able to get up to our pressure, say, as quickly. So limitations that are impacting your process today possibly could impact our process now. If you don't have any existing limitations on your machine and product, then I wouldn't anticipate we would create any new ones. If anything, it would be easier. But really, the molding machine, nothing needs to be done to it. We're just going to add our adapter. We're going to add our controller so we can talk to your screw. You'll get the interface to set the process up.
So it's the system completely installed on the machine side, right? No in-mold
Yes.
sensors or.
Correct. Yep. Everything's on the machine. We don't have to install. Like I said, if you have sensors on your mold, we'll use them, but it is not a requirement. This is a machine side solution, not a mold side solution. Which is nice. Now you install iMFLUX on your injection molding machine, you can take advantage of it across every single tool that runs in there.
Can you talk about the response time of the screw or the plunger, right? Speed that you need. Does
Yeah,
it limit
so-
the size that can be used?
There's no limitation on the size. As far as scan rates, every millisecond we're scanning to make adjustments if that plastic pressure isn't at set point. But also that's where the tuning comes in. So, you're out of the box, or the tuning parameters of your machine today probably won't be able to replicate the process as we would like it. So we do want to have ability to tune that press to create the curves we're looking for. And that would be another part of it. But again, that's completely customizable. You can actually tune it by mold if you want to. You have all that capability in your hands.
How many shots will the transducer last?
Millions? Yeah, I mean, we've, especially in the olefin side, boy, we've been running these things for a very long time without issue. And even in the glass-filled nylon side, we have customers running today the system, some pretty nasty environments with not issues. If anything, it's external. External problems are probably our biggest problem. Someone stepping on the sensors more than the internal.
How many of these systems are out in the marketplace outside of PG?
Outside of P&G, hundreds. Hopefully it'll be thousands soon, but I'd say hundreds. And the breadth of the industry that we've been able to work with is kind of fun and impressive. It's everything from the P&G high packaging products to heavily recycled large products like the pallets I was speaking of, or large industrial containers, large agricultural containers, down to consumer electronics, valve and pump components, things that are made of nylon, things like that. Automotive industry, everything from door panels to visors to rear hatches to tractor fenders. We've had a lot of success on a very wide breadth of the industry.
Do you have a history of running in the connector industry, and maybe some of those engineering grade resins, the PBT?
Yes.
Yeah.
Yes, we do. Yes, we do. Yep.
On a typical implementation, right? There's a couple questions here regarding a range on the cost. Are you free to give a range for an implementation cost?
60 to 70,000 is going to be probably what you're going to be charged for the box and everything. Now, if there's work that needs to be done on the machine manufacturer side, so let's say to talk with their software, there may be some additional costs there. That's where we would work with you and your OEM to make sure we give you the optimal solution.
Is the compensation tied to a one-time purchase?
Yes.
Okay, how about a little bit different range here, but how about on the medical device molding? Can it be validated?
It can, yeah. Our software has gone through the medical validation requirements so that it can be utilized. We have multiple medical device customers that are using the system today. And I mentioned it earlier, from the medical side, I think they get excited about the how much less variation they're seeing across their cavities, right? So in the medical world, you typically, it's pretty rare to see over 16 cavities. As they know, right, as their cavitation grows, it's harder to control quality. I think our customers are experiencing that necessarily isn't the case anymore with iMFLUX. They can start looking at adding more and more cavitation and having a much smaller distribution of dimensional data, the dimensions across those cavities than what they're used to seeing. So they're not so tightly controlled, especially as the manifolds become larger and larger piece of our industry, right? There's never going to be a hot runner that's as well balanced as a cold runner, just by physics alone. And so even you're starting to see more medical molders going the hot runner route, which makes sense from a waste standpoint, but not great from the cavity balance standpoint, right? Hot runners turn on and off, on and off. Cavity 1 is the first to fill today, but maybe it's the last to fill next week, sort of scenario. Multi-process disease, as it's called. That's not going to impact our process, right? All those cavities are going to see, the same pressure every single shot.
Excellent. How about like the micro molding world? You guys got?
Yeah, more to do there, honestly. Just like the LSR. Again, it's going to come to probably having some really good partners, maybe Sodick can be one of them, to help us expand on the micro molding side. Again, it's not something I have here at my R&D facility to kind of mess around with, but again, it's an area we definitely are looking to expand into.
With all the areas that you have already expanded into, or maybe considering, what kind of application would not be a good application for you?
If I had to choose one, maybe like PET preforms, just pick one. Again, mostly because we need to do a lot more work there. It's a huge part of the industry. I would almost not call it injection molding. It's kind of its own thing, right? You never see a PET machine running general purpose molds, and vice versa. So we need to do more homework on the specialization of PET and intrinsics, viscosity, IV and all those fun parts of it. That's just different than normal, and it's really just us getting the chance to learn more about those systems and then actually apply our technology and see how it works out. Again, those opportunities have been limited.
Wonderful. A couple more around the speed here.
Sure.
One is how fast you inject with the iMFLUX with unfilled nylons, and following that up, maybe what's the fastest cycle time part that iMFLUX is running on?
Fastest cycle time, probably 4 to 5 seconds. We can do very high speed packaging stuff. We do it all the time. So probably around there. As far as velocity, we can go as fast as the machine will allow you to go, to be honest. We only want to go as fast as it needs to go via the pressure. So it's kind of hard to answer that specific to nylon without seeing more about the part. I would just say, like, whatever your machine's capable of achieving velocity-wise, we can go just as fast if we need to. Doesn't necessarily mean we need to, but the capability's there.
Excellent. Got multiple cases of this question, okay? And maybe it's something that you would want to follow up on, Brandon, later, but people wondering if there's a way to sample one of their tools, right? Maybe before acquiring a system. What would be the process? And maybe that's where I can get you these names.
Yeah. So we have a great facility here in Hamilton, Ohio, just outside of Cincinnati, a very large facility where we love to trial out your tool for you. We have 12 injection molding machines here. So hopefully we have something that fits you. Our largest press is 500 tons. So if you're getting into a really large product, we would want to, do that maybe at your place. But yes, we definitely, if I was sitting in everyone else's chairs, I'd want you to prove it to me, right? Before I spent any money.
Right.
And we completely understand, and we want to do that for you as well. So we do offer trials. They're not expensive. We keep them, pretty low so you can get a taste of the technology. And then we can either do that in-house or, if we don't have the machine to accommodate you, we can set something up at your facility as well. But yes, we we anticipate and we're happy to do trials.
So just to reiterate, you can do them in your facility or on site, possibly.
Yes. Yep.
Okay, excellent. Pushing up here on the 2 o'clock hour, a couple more questions coming in. Are mold venting strategies different?
Yeah, great question. Yes. So one of the things with lower pressure is it unlocks the ability to do some other things in your process you may not otherwise do. So some of those include lowering melt temperature or lowering clamp tonnage or making your vents bigger. I'm not going to flash your tool as easily because I'm operating at much lower pressures, especially once you hit that transfer position. So the vents you cut today, you could probably cut a little bit bigger because I'm not going to have the propensity to flash into those vents. And if you can use lower clamp tonnage, your vents are going to live longer. And iMFLUX has a hard time flashing your tool, to be completely honest with you. And you saw in the one video where we'll just block cavities in real time. It's pressure and time. That's all it is. It'll fill up whatever's available to fill up in the tool. But if the tool suddenly changes, it'll accommodate that in real time automatically. Imagine, I'll probably give some tool engineers some nightmares here, but imagine not turning your hot runner system on and you go to let rip your first shot. You're going to have an absolute mess in the conventional molding process, right? Because the machine doesn't know anything. It's doing exactly what you asked it to do. It's going to go at 3 inches a second until it hits that peak pressure and then probably alarm out. iMFLUX won't even inject. We'll hit pressure immediately and it'll just stop. Again, because the mold's controlling the process. If I drop 1 cavity, 2 cavity, 5 cavities, it doesn't matter. It's the pressure and time. I'm not going to shove whatever materials between my shot size and transfer position in that mold, no matter what. So it's intelligent in that way, and it's a lot better for your tool longevity as well.
Wonderful, great stuff here. Looks like that was our final question. Maybe we'll give a couple more minutes here. If there's any other maybe last thoughts that you have that you want to share, Brandon.
No, just again, thanks to the Sodick team for having us. We're super excited to be here and share this with you guys. Sustainability is a big piece of a big area of focus for everyone in the industry. Anything you can do to generate more flexibility, and when you're considering part or mold design, a lot of part prints say use this material. Imagine a future where it says I can use any of these 4 or 5 resins, and would allow you to qualify all those in real time with the exact same process. We'll just have it modulate the pressure as needed for the material. You're going to build a lot more flexibility into not only into your organization, but ability to handle events you can never predict, like a hurricane hitting Houston, for example, and not able to buy polypropylene. This iMFLUX automatically makes your process provides you more flexibility, more adaptability, and is not going to ask your operators to be standing press side all day long, trying to handle the variation coming in. We want more molders to use more recycled resins and bring variation and let iMFLUX handle the variation for you so that you don't have to pass that liability onto your customers. We want to eliminate that liability through intelligent processing, and that's exactly what we're all about. So, we're really big on the sustainability side now, and it's a big focus of ours. So anyone out there, that wants to run more post-consumer regrind or post-industrial regrind or more wide spec resins, give us a call. We have a phenomenal solution for you that can't be matched in the industry. Not right.
Brandon, maybe you could flash your back page if people want to take a snapshot of your contact information.
You got it.
Real quick, I know that was fascinating talk today, and I know we have several customers, in optics, medical device for sure, and drug delivery, and it's great working with you folks. Very talented group over there at P&G iMFLUX. So thank you so much. Really appreciate it.
Absolutely.
Yeah, just to reiterate that, Brandon, thank you very much. everyone that attended today. Really appreciate you taking the time out to hear about iMFLUX. Thanks for joining Sodick and Friends. And I guess with that, everybody have a great afternoon.
Okay, great. Thank you.
Thank you, Weston. Thank you, Bennett.
Happy 4th of July, everybody. Take care.
There you go. See you, folks.